This is the chapter of electrodynamics especially for the engineering students. Uh, Name of the unit is electrodynamics. So before we go into the detail of the electrodynamics and mainly for the Maxwell equation and electromagnetic waves, I have to study basically the basic fundamentals of this chapter, that comes basically through the four laws, that is Gauss law in electrostatics, Gauss law in magnetism, Faraday law and Ampere's law. So in these laws basically we know that electric flux, charge, potential, magnetic field, magnetic flux, these are the important scientific words. So what is the physical interpretations of these scientific words and other related information that will be beneficial before we go into the detail of this electrodynamics chapter. So this is the electrostatics and electrodynamics. We know that when charge is in a stationary form, that treat under the electrostatics. Basically a stationary charge, if suppose this charge is in stationary form and I am saying this is plus Q charge, so it basically a field develops. That field is represented by the vectors. So a field develops around this positive charge and electric field lines start into the space. These electric field lines basically ends up to this point, that is negative charge Q for an example. So up to this point we saw the electric field lines with the help of the arrow, which indicate to the negative sign. So these electric field line basically which starts from the positive charge behaves like a source and ends up to the negative charge that behaves like a sink. So these fields basically here nearby to this positive charge and nearby to this negative charge, this is an electric field. So the properties of these electric fields, for an example I want to measure the potential realization of the electric field, number of these electric field line in terms of the electric flux. So electric field and electric flux and that charge where these electric flux is associated, we studied into the electrostatics. And what is the electrodynamics? In electrodynamics basically when charge starts to move, a moving charge, basically what this moving charge do, this moving charge basically produce a magnetic field. Moving charge produce a magnetic field. So we have to study basically the property of the charge when charge is in stationary form and when charge is in the moving form. So a stationary charge produce the electric field and moving charge produce the magnetic field. So it means there is some connection between the electric field and magnetic field. So we will try to develop that relation between the electric field and the magnetic field. So in the here method to measure the direction and magnitude of these field mathematically. We know the electric field. We have seen that in case of positive charge, this is the electric field lines. We are saying these are outward in reference to the closed surface. Suppose we consider a sphere like this one. This time we are showing electric field lines outward from the positive charge. Is there any mathematical formulation with which we can say that the electric field line direction. We can measure the magnitude of these electric field lines. Yes, that we have some mathematical methodology to measure the direction and the magnitude of this electric field. You know that these field lines are not always straight form. If suppose we know that this electric field line starts to move into this space. If suppose a negative charge is far away from the positive charge, then after some distance these straight lines basically becomes into the curved shape. Now the electric field lines will be into the curved shape. So how to measure this curve and this direction? So that comes basically into the curl with the help of the curl operator. If the electric field lines are straight, then we can measure that electric flux at any point with the help of the divergence. But if suppose we have to measure such kind of electric flux where we are observing the curvature, then we have to use curl operator. So here this positive charge basically behaves like a source and the negative charge behaves like a sink. So at the emerging point and converging point you can see and observe the field lines difference. So what is happening basically at the positive charge, electric field lines are emerging, and at the negative charge here these electric field lines are converging. So how to study the behavior of these electric field lines? These are emerging electric field lines, these are converging electric field lines. Is there any methodology to identify this type of nature of the electric field? Yes, that we can find out with the help of the divergence. If the divergence is positive, then we say the electric field lines is outward. If divergence is negative, then we say the electric flux basically is inward direction. So with the help of the closed surface we can explain the negative and positive divergence. But what about the zero? Because with the help of the divergence we can measure the magnitude of the electric flux or magnetic flux. So the result of the divergence of any vector field function is a scalar quantity. That means we are just measuring only the magnitude, and magnitude can be 0, positive or negative. So now we have to see basically the interpretation of this result one by one. But before that we have to know about the nature of the field. Field are of two types. One is a scalar field or second is vector field. So how to decide the field nature? This field will be scalar or that field will be vector. This basically decided on the basis of physical quantity. If the physical quantity is scalar, then we say the field will be scalar. If the physical quantity is vector, we say that field will be vector. So for an example, if we consider temperature is a scalar quantity, but in a room we can measure temperature, and temperature will be different at different points. So temperature is a function of the spatial coordinate x, y, z. So T is a function of x, y and z. So that basically field, that is the field of the temperature. Now this field will treat under the scalar field concept, and vector field, electric field and magnetic field both are the vector fields. So a field may be scalar and vector. It depends on the choice of the physical quantities. For an example, temperature is a scalar quantity, so that field will be scalar, and that field is known as the temperature field. So here I just try to show the nature of the field. This is positive charge, and in the surrounding of this dark, and then after it becomes light. Here dark and it becomes light at this end. So this is the area, this is the basically area, this is the field of the electric potential around a positive charge. If I have a point charge, suppose I have this point charge here, so I realize a force. Okay. It means from wherever I start to realize a force, that is the area, that is the field of that charge. So this is a field of the potential, that is a scalar, and on the other hand this is the field, this is the electric field of the positive charge. Here temperature is shown, the dark, slightly dark, light, and this is almost white. So here the dark portion basically indicate to the high temperature, and light one is the lowest temperature. So the direction, now the question is the direction. This is the high temperature and this one is the lowest temperature. So this is the field of the temperature, this is the field of the potential, and darker region basically representing the higher values of the potential or of the temperature. Here we have considered some basic example to explain the field, vector field, especially in case of charge, electric charge, in case of magnetic poles. So you can see here, this is the positive charge, this one is the negative charge, and these are the electric field lines, and this is the closed surface around this negative charge and positive charge. Surface is closed, and in between of this positive and negative charge we have considered here open surface. So here we have just tried to show potential, the divergence of the electric field will be positive, divergence of the negative field is, divergence of the electric field is negative, divergence of E is less than 0. Here at this point we are saying that divergence of any vector field, and that vector field which we are considering here, that is electric field. So divergence of the electric field is positive. Positive, why positive? Because electric field lines, electric flux is outward. Outward, we are using this outward in reference to this closed surface. Here electric flux is inward direction, and this inward is in reference to this closed surface. So this is the nature of the electric flux, electric field. Here outward, here inward. So outward basically indicate to the positive divergence. Here inward flux represent to the negative of the divergence. So when we take the divergence of the electric field vector or magnetic field vector, basically we are just measuring the magnitude of that field at that particular point. So this could be negative, this could be positive. So what we have to conclude on the basis of this result, which we are getting positive, negative. So positive means ki flux is outward, and negative means flux is inward direction. But we have seen that a result of the divergence of any vector field function might be 0. So what is the meaning of 0? If suppose divergence of E of any vector field function is equal to 0, what will be the meaning of this equation? This equation basically the result, when we have to explain of this equation, for that we have to consider a open surface. Now keep this open surface in between the positive charge and negative charge. So the electric field lines which enter through this open surface are equal to the number of field lines which are coming out from the other phase. So the total electric flux is equal to 0, which you measure at this point. So divergence of E is equal to 0. At this situation, this vector field function is known as solenoidal function. So this is the physical interpretation of this mathematical equation. When you take the divergence of any vector field function, you basically get a result in terms of a magnitude of that field. That magnitude might be 0, positive or negative. Now the question is, what is the physical interpretation of these results? Then we can say, when the divergence of any electric or magnetic field function is greater than 0, we are measuring the outward flux. When divergence of electric flux or electric field is less than 0, we are saying that electric flux or magnetic flux inward nature. When divergence of electric or magnetic field function is 0, we are saying that total electric flux is 0, which we have measured. Why? Because the total number of electric field lines which enter through this open surface are equal to the number of lines which are coming out from the other end. But in this situation, this positive charge, and here we are considering a sphere, and this charge is kept at the center of the sphere, so electric field lines basically are coming out. And here at this negative charge, this is again same sphere, but at the center we have kept this negative charge. Here all the electric field lines basically are converging at this point. So this is the physical interpretation of the result. We can use this divergence at electric field or at magnetic field. Divergence of B. Here divergence of E. So with the help of divergence, we can measure the magnitude and the nature of the field. This electric flux is outward, inward, or what type of that. So here this is north pole, this is south pole, these are the magnetic field lines. So we can measure at any point the direction, the nature of the magnetic field lines and the magnitude with the help of this process, mathematical process, by taking the divergence of that field. This is an example of hurricane. We will see it into the curve. So now, before we go into the detail of the this process, how to measure the electric flux and how to measure the direction, in case of when electric field lines are straight and when these electric field lines or magnetic lines are in a curved shape. So we have three mathematical operators. One is the gradient, second is the divergence, third one is the curl. So first mathematical operator which we have to use, that is gradient. Second is the divergence, and third one is the curl. These are mathematical operators, and we have two fields, a scalar field and vector field. These are two fields. So what we have to do, basically we have to operate these operators on these field functions. These field, scalar field and vector field, basically we will treat these field like a function fx. So as we have seen earlier that we were saying temperature is a scalar quantity. So temperature basically is a physical quantity that develops a field that is known as a scalar field, and T, temperature, is a function of a spatial coordinate t, x, y and z. So at every point basically in space temperature will be different. So here T is a function of spatial coordinate x, y and z. So second point is the electric field and magnetic field. These are vector field. So T is a scalar field, electric and magnetic field are vector fields. These are the operators. Now what we have to do basically, first we have to develop mathematical formulation, a mathematical development to study the electrodynamics. So for that purpose we have these operators, we have these fields, and we will treat these fields like a function. So we have to operate these gradient, divergence, curl operators on the field function. So gradient, the first point is gradient operator always operates on the scalar field function. Gradient operates on the scalar field function. Divergence and curl operates, these two operators operates on the vector field function. So how to write gradient? This is the gradient operator, the way of writing gradient of T. So this gradient operator operates on the scalar field function, that is temperature x, y, z. This is the way of writing. You can write this in this form, del operator, with the help of del operator, del T, where del, this del operator indicate the expansion of this del operator is del upon del xi plus del upon del yj plus del upon del z k. This is the expansion of the gradient operator. When this gradient operator operates on this temperature field function, which is a scalar quantity, it basically provides a vector quantity. So when del operator, this del operator on this T, which is again a function of x, y, z, so it becomes del T is equal to del upon del x Ti plus del T upon del y j plus del T upon del z k. So if you write T here, this is T, this is your gradient operator, del operator, and this one is the T. So T will be here, here, here. So d del T upon del x I plus del T upon del y j plus del T upon del z k. So this is the variation into the temperature component along the x direction. This is the variation along the y direction into the temperature, and this is the variation into the temperature along the z direction. So this del operator, when operates on a scalar field function, it provides basically a vector field function along the I direction, along the j direction, and along the k direction. So now this result is basically a vector field function, and through this del T upon del x we can find out the magnitude, and with the help of this I, j, k we can find out the direction. So what will be the direction? In case when we take the gradient of any scalar field function, the direction will basically towards the maximum change. Maximum change is occurring towards the high temperature. So this will be the result of this gradient operator about the direction. Now next point is related to the gradient. As I told you earlier, that gradient of a scalar field is a vector field which points in the direction of the greatest rate of increase of the scalar field, and whose magnitude is the greatest rate of change, that change basically towards the darker side. So this is a best example to explain the gradient, the direction. Here in case of the potential, so he has taken the gradient of this potential. So direction basically is indicating to the maximum change towards that the center. Here maximum change is towards the higher temperature. So in the above two images, the scalar field is in black and white, black representing higher values and its corresponding gradient is represented by these arrows. Note it, phi is a scalar field function, and when you take the gradient of it, the way of writing is this: del phi upon del xi plus del phi upon del yj plus del phi upon del zk. Even though phi is a scalar, the gradient of phi is a vector quantity. The expression of gradient phi can be written as in this way: gradient phi, this way, expansion del phi, this del phi, where this del is basically is correspond to this one, is a called del operator or nebula. So this was the meaning of the gradient operator when gradient operator operates on the scalar field function. Next is the divergence operator. Divergence and curl operator, as I told you earlier, that operates on the vector field function. So this divergence of a vector field, what is the meaning of this? When you take the divergence of a field, what basically information you are collecting from that? We have discussed earlier that when we take the divergence of any vector field, we just are measuring the direction and the nature of the field. We are just measuring, sorry, not direction, the magnitude of the field and the nature of the field. Divergence is an operator that measures the magnitude of a vector field source or sink at a given point. The divergence of a vector field is a scalar, and at a point it is defined as the amount of flux diverging from a unit volume element per second around that point. It is a scalar product of del operator with a vector field function. When you take the divergence of vector field function, basically you are getting a scalar result. Scalar means only magnitude.